Hello and welcome to NPTEL MOOC on Applied Electromagnetics for Engineers. In this module, we will first finish an example of finite difference method that we discussed in the last module, and then discuss another numerical technique called as method of moments. So I hope you remember what we discussed in the finite difference method. If you choose your step sizes appropriately, then the potential at any point will be the average of the potential of the neighboring 4 points. So if for example the point I need to find out the potential is given by this dot, then the potential to the left, potential to the right, potential to the top and potential to the bottom are the ones that you need to use and then average them, provided the sizes or the step sizes from the point where you are calculating the potential to the point where the potentials are known, that step size will remain same. So this step size thing will actually become independent when you actually calculate using the finite difference method. So here is an example which is a conducting trough. We have already looked at the analytical solution of this one in the form of a strip line with a finite strip that we had kept. It was actually a two parallel plate wave, and it was a parallel plates that we had kept, two plates in parallel we had kept, and then we had shorted the two plates by an appropriate conducting strip, and then we had calculated what would be the corresponding equipotential surfaces or equipotential contours as well as what would be the electric field. So I would ask you to go back, in case you have to follow the next few steps, I would ask you to review whatever we have discussed in terms of the earlier example, so that you can see how the analytical solution can be obtained from this numerical solution. So we start by the problem that is shown here. So all these colors of the lines that I have made, they are all supposed to represent ideal conductors. The top conductor is kept at 100 volt and the other three conductors, which are all joined together, are kept at 0 volt. Of course you need to put a small gap, otherwise everything will be on the same potential. So we put a small insulating gap so that the top plate is at 100 volt potential and all the other plates are at 0 volt potential. Now what we want is to solve this Laplace's equation inside the empty region that we have, and then determine what are the equipotential lines. Once we find what is the equipotential lines, then either by graphical method or by a computer method you can easily find what would be the electric field, because electric field will be perpendicular to the equipotential lines. So let us dig into this problem. So you have 0 volt, 0 volt and 0 volt. So in the first iteration I actually want to determine the potential at the center point here. To do that, I need to look at what is the potential onto the left, which happens to be 0, potential onto the right, which is 0, potential on the top, which is 100, and potential at the bottom, which is 0. So the first potential that I will be obtaining will be given by 100 plus 0 plus 0 plus 0 divided by 4, and that you are going to obtain as about 25 volt. So this is the value. The first time that you are going to write will be 25 volt. So this seems to be very simple. Now what we do is we need to find out the potential at other points. Suppose I try to find the potential at this point. I know what is the potential to the left, I know what is the potential to the right, but I don't know what is the potential onto the top, because remember, this step size was equal to this step size. However, the step size is now reduced to half. So if I want to find the potential at this cross point, I need to know what is the potential at this 0 point or this particular point, which I don't know. So what instead I can do is that I know that the potential at the gap is going to be 100, or the top conductor will be about 100 volts, but I can find out what would be the potential at this gap. So this gap potential will be the average of these two neighboring points. So if I am trying to find out what is the potential at the gap, it would be of the neighboring points. This time I have only 2 points here. So I have one point here at 0 volt potential and the other one is at 100 volt potential. So the gap can be written as 100 by 2, 50 volt. So we make an initial guess that this would be 50 volt. Of course this is just an estimate of the potential that would be present. In fact, you would see that there would be lot of the potential has to go all the way from 100 volt on the red line to 0 volt on the blue line. Therefore there will be many such potentials that need to be calculated, but for now you can assume that the gap potential that we estimated is 50 volt. Similarly, we remove this gap over here and then say this is also 50 volt. So now we have slightly more information about the potentials. So we might want to calculate the potential at other points. Okay, now let us take this particular axis. Okay, so essentially what I mean is that we have turned around the x and y axis by about 45 degrees, and I seek the potential at the center over here. Now to this potential, if now imagine yourself turning around or turn the paper around in this way, if you are calculating this on the piece of paper, you see that the potential to the left is 50 volt, potential to this one is about 25 volt, potential to the top here and the bottom here will be 0 and 100 volt respectively. Therefore, the potential at the cross point that I have made, which would also be the same potential here, because it would also be by symmetry the same potential. So the potential at the cross point which I have made will be an average of 50 plus 100 plus 25 plus 0 divided by 4. So this would be about what, 175 divided by 4. I don't really know what is the value, but you can actually calculate it by a calculator and then put that one. So that would be the same value over here as well. So this would be 175 by 4. This would also be 175 by 4. I will rewrite this one in a neat manner so that you can see this correctly later on. But for now, look at what is the potential at the green color over here. Again, I have a potential to the left which is 0, potential to this one is 0, potential here is also 0, but the potential on the center of the trough is 25 volt. Therefore, the average here or the potential at this point will be 25 by 4. By the same symmetry, this potential will also be 25 by 4. So after 2 iterations, okay, so after 2 iterations, the potential would look something like this. The grid potentials would look something like this. So let me redraw this one. So this is slightly bigger picture that I am going to draw, okay, and then I have the top conductor which is kept at 100 volt, and I have 50 volt at the gap, 50 volt at the gap. At the center I have 25 volt, and so this is at the center that I have. These potentials are 0 volt, 0 volt and 0 volt. We have also calculated the potential at this point, which is 175 by 4. The potential at the center of this square is 175 by 4. The potential here is 25 by 4. The potential here is 25 by 4. Now I have reasonably more number of points. I can now find out what is the potential at these cross points, okay, which are essentially at the center of these 2 points. Now that would be the potential at this cross point would be 175 by 4 plus 25 by 4, because these are on the, if you think of this, this is top, bottom, to the right and to the left. To the right will be 25, to the left will be 0, this entire thing divided by 4. And again by symmetry this would be the same value over here, so you get additionally 2 more points. So by looking at this one, you are able to get additional points over here. So if you actually continue this, okay, this of course will be different, but if you continue the entire grid, what you would see is that the potentials will actually be larger over here. This would be say 50 volt contour, so this would be a 50 volt, then the potential actually starts to drop. This would be a 25 volt contour because it is actually passing through the center with a 25. This potential will be whatever 25 by 4 point, and then this would essentially be very, very small, so that this is approximately 0 volt. Of course, the actual 0 volt potential is is given by the walls of the conductor. So this is the method by which you can actually calculate the potential in a complicated scenario. I want to add one important point. The potential that we have calculated in this manner is okay for a paper and pencil calculation. This is strictly speaking not the way on a computer that we are going to implement it. On a computer we would write the d square v by dx square, whatever the equations that we obtained, after approximating the derivative in terms of those 4 values that we obtained, and the right hand side is either 0 or at the boundary we will have to take care of a little bit of a problem out there, but we have to take care of the boundary and convert this entire thing in terms of a matrix equation. So you will have the matrix corresponding to d square v by dx square on the left hand side, okay, and then this would be the v, actually this would be the matrix corresponding to the operator d square by dx square times v, that must be equal to some boundary condition plus most of these values will be equal to 0, and then you proceed to solve for a unknown potential values v, which you have tried, which you have marked out there by either a matrix solution, okay. we will follow a very similar method in the next numerical technique that I am going to discuss, and that technique known as method of moments. To introduce method of moments, let us begin with the actual problem. I mean the problem in a slightly simpler context. We have seen that Laplace's equation tells you that del square V equal to 0, but Poisson's equation tells you that if there is a charge distribution in the region, then this del square V will be equal to minus rho by epsilon. And this del square V equal to minus rho by epsilon, where rho in general can be a volume charge density, always has a solution at any at any field point r. Okay, so this is your field point. This is the position vector of the point at which we are considering the potential. This always has a formal solution. Okay, so this formal solution is an integral over the charge distribution, the charge distribution in the given region. So for example, this is the region where the charge is distributed. Okay, so any point at which I am actually evaluating the potential is called the field point, and the corresponding position vector for the source point will be denoted by a prime on the letter r. So you have rho of r prime, which is a scalar field, of course, and of course it's a function of a vector r prime, but the result is actually a scalar over the volume dv prime occupied by that particular region over there that we are considering, divided by 4 pi epsilon r minus r prime magnitude. Okay, this r minus r prime will be the line that joins the source point, the point where the charges are located, to the point where you are calculating the field. Okay, this can be line integral, volume integral, or a surface integral depending on what type of geometry that you have. So given rho of r prime everywhere in the region, it is a reasonably okay matter. I am not saying it is very simple, because someone has to carry out this integration, and this can be even done numerically, but if this source is given, then it is rather trivial matter to determine what is the potential at entire space. Of course, the problem is that you are only allowed to specify potentials in most of the cases. You can specify the voltages at different points in the conductor in most of the cases. You do not know what is the charge distribution. So if the charge distribution is unknown, how do we calculate the we know the potential at certain points only, then we need to calculate the charge distribution. Once the charge distribution is known, then the potential at all the other points where we have not specified the potential also has to be calculated. The method that we are going to adopt is what is called as method of moments. Okay, a full discussion of course will take you into a different course on numerical methods which are running in NPTEL. You can refer to that, but a brief idea of method of moments is like this. In order to understand this method, we will look at a simpler problem. Okay, we consider a very thin wire. The wire has a diameter of about 2a, okay, and a certain length which is much larger. So this, let us make it as a capital L. So this length L is taken to be much larger than the diameter. So essentially what we are considering is what is known as a thin wire. Okay, the radius a or the diameter 2a is very small compared to the length L. Okay, let us say there is some unknown charge distribution. You do not know what the charge distribution here is. There it was you are trying to calculate. Okay, we also let this wire lie on the x axis. Okay, so the wire is lying on the x axis, this other axis is the y axis. For now, this is the two-dimensional picture that I can show you. What we do here is we reconsider that wire. Okay, so you had this wire which was extending over say minus L by 2 to plus L by 2. What we do is we section this wire into appropriate sections. Okay, we cut this wire, not actual wire and then cutting it. We imagine that the wire has been cut and there are different sections, section 1, section 2, section 3 and so on and so forth up to the last section N. Okay, this is the y axis. At any point, for example, if I want to find out the potential at the point P marked here, there is a certain position vector to this which is r, and if I consider the charge on a particular section, right, so there will be n number of sections over here. If I consider the charge in a particular section, the charge itself will have a certain potential vector r prime, and from the charge to the point P will be the joining vector r minus r prime. Okay, so please note that r prime is what is called as the source position vector, r is called as the field position vector. Okay, what we are interested is not r or r prime themselves, but the difference between these two, which we will designate by some capital R, okay, a vector R if necessary. Okay. Now what we assume further is that within this particular section, here it is a section 3, but it can in general be any one particular section J. Okay. In this or ith section, in this section we assume that the charge distribution is going to be constant. Okay. For now, neglecting that this is actually a volume, because this is a conductor, most of the charges are actually residing on the surface. So what you are actually calculating is on the ith section, what is the unknown charge rho si, and this rho si will have a certain position vector ri prime, or because I am having an x axis and a y axis defined, and I am assuming that the thickness of the wire is very small, ri prime is approximately xi prime, that is I am measuring the position along the x axis. Okay, as I go through that, this times whatever the surface charge density that I have, delta Si, will actually give me the charge, total charge on the ith section, okay, which we will assume to be constant. So charge on the ith section assumed to be constant. Of course, this rho Si, which is given at that particular ith section, is completely unknown to us, but it is essentially considered to be a constant. So the potential at the point R, which is the point P, can be written as 1 by 4 pi epsilon naught. This is actually just a constant, so you can pull this constant out. You can even set this constant equal to 1 and reintroduce the constant wherever you want, but let us not do that. And now how do I go from a continuous to a discrete? Well, if you remember the definition of an integration, okay, integration is actually made out of small pieces, multiplying the values of the particular function and multiplying it by the width and then summing them over. So you have an infinite number of such summations that will result in a summation going into a integration. But on a computer, I can't do an integration directly, so I will always have to do a discrete version of that, which essentially is a summation. Okay. So the summed value, the potential at this particular point R, is given by sum over all the sections that I have. So I have made n sections of the wire, so it would be I equal to 1 to n rho Si delta Si divided by xi minus, so we run into a small problem here because I have to specify not the potential at this point R, okay, as I thought I would want to, but I would like to determine what is the potential at this particular point, which would be say xi. Okay. So if I want to do that one, then instead of considering a general point R, which would be in the xy plane, I am trying to find out the potential on the wire. Okay, I will tell you in a moment why I am trying to do this one. The potential at the point xi, because I have used the index I for this one, I have to change the index over here. So let me change the index. So instead of talking about the ith section, I will be talking about the jth section. Okay, so I have j equal to 1 to n rho sj delta sj. Delta s is the surface of a cylinder, okay, whose diameter is about 2a and whose length is delta li, where delta li is the length of each section. We of course have made n number of sections, therefore delta li is equal to capital L divided by capital N, that is the length of the wire divided by n. So I have rho sj delta sj divided by xj xi. Okay, I don't need to put prime over here, at least, or maybe if I want I can always put a prime over there. Of course, if I put the prime here, I should put a prime del sj prime and rho sj prime, but I will not put those primes just to confuse all of us. But it is very important to note that this particular expression that we have written will be evaluated at a constant xi, that is on a particular ith section. Okay, of course this I itself has to go from 1 to n. So let us actually write it down completely. Oh, before we do that one, I want to specify why why I wrote the potential at the center point xi on the wire. Because this is a conductor, I actually set the potential of this conductor. Okay, so I set the potential of the conductor to some value. Let us say I set the potential entirely to 1 volt. So how do I do that? I of course have to take a a battery or something and then correspondingly connect a 1 volt battery to this particular wire. When I do that, the entire wire is assumed to be uniformly at a same potential and that value is taken to be 1 volt. Just for our simplification, it could be any other potential. In fact, the potential could also vary. That doesn't really change what we have written in this equation. Okay, so that's the beauty of a numerical method. You can make V of xi be different at different sections. Okay, now that we have written here j goes from 1 to n, I also goes from 1 to n. Let us completely rewrite, let us write for all values of I what would be the corresponding expression, and you can very easily see that for I equal to 1, that summation sign has to be expanded, and what I get will be 1 by 4 pi epsilon, which is a constant, times rho s1, this is on the section 1, and I am looking at the potential at x1 itself because of x1, plus the charge on the section 2. The point where I am evaluating the potential is still x1, but the source is located at x2, that is on the x-axis it is located at x2. Similarly, you get rho s3 delta s3 divided by x1 minus x3 all the way. Let us go up to rho sn delta sn. So this is not visible out there, so let me just rewrite it below here. So this would be going all the way up to rho sn delta sn divided by x1, that is still the point where I am calculating the potential, minus xn magnitude. Okay, for I equal to 2, it would essentially be the same constant 1 by 4 pi epsilon naught. Then you have rho s1 delta s1, which is the charge on the first section, divided by x2 minus x1. Why? Because this is the field point at which I am actually evaluating the potential, and this is where the charge or the source is located. So if I carry out for the last section, I get rho sn delta sn, which is the charge on the last or the nth section, divided by x2 minus xn, and so on. Okay, I can put everything together in terms of a matrix. Okay, that would be very interesting to look at. In matrix notation, this would be delta s1 x1 minus x1 magnitude, delta s2 divided by x1 minus x2 magnitude, so on up to delta sn divided by x1 minus xn magnitude. You go to the last section, which would be delta s1 divided by x capital N minus x1, which is a section 1, then delta s2 divided by xn minus x2. Okay, go all the way up to the last section, you get delta sn divided by xn minus xn magnitude. Okay, so this is the matrix which will be n cross n matrix. Okay, you can put a shorthand notation of this matrix as some Z matrix. Okay, Z matrix is this one. What is the unknown vector? Rho s1, rho s2, all the way up to rho sn. These are the values which I don't know, so I put them as a n cross 1 unknown vector. Finally, onto this side I have all these constant, which is 4 pi epsilon 0, 4 pi epsilon 0, 4 pi epsilon 0. Why is this? Because I know that the potential at I equal to 1 point will actually be equal to 1 volt. Similarly, the potential at the second section will also be equal to 1 volt, because that is the voltage that we have set on the wire. We have set the voltages and the voltage is set to be uniform. If it is not uniform, then you can write the appropriate values of the potential, whether it is 1 volt, 2 volt, how you have defined the potential. In this case, the potential at all the sections is equal to 1 volt. Therefore, this 1 by 4 pi epsilon naught, when you take it to the right hand side, simply becomes 4 pi epsilon naught. So now I have a very interesting matrix out there. Okay, there are two things that you would immediately recognize. Okay, if you look at the diagonal elements are all going off to infinity. Why? Because there is an x1 minus x1, which obviously will be equal to 0. So this diagonal element will shoot up to infinity. Similarly, there will be x2 minus x2 in the second row, second column, that will also shoot up to infinity. The last row and the last column will be having xn minus xn, which is again 0, and therefore this will also shoot up to infinity. That is the first observation that you are going to make. The second observation is the value delta s2 by x1 minus x2 will be similar to to the value that you are going to obtain in the other case. This would be the matrix that we have written. So you will have delta S1 here divided by x2 minus x1. So apart from the delta S2 part, 1 by x1 minus x2 magnitude will be the same as 1 by x2 minus x1 magnitude. Okay, the top will also be the same because we are going to assume everything to be having the same surface area. Therefore, the matrix essentially will be symmetric. It would be symmetric such that upper diagonal elements will be equal to the lower diagonal elements. Okay, so you have a matrix which is symmetric, which means if I take the transpose of this Z, then I obtain Z transpose will be equal to Z itself, and further the problem that all these diagonal elements seem to go to infinity. So how do we overcome this problem of infinity? I will not completely give you the way in which it is done. The idea is that if I blow up one section of whatever the section I am looking at, then I know that I am calculating the potential at this point xi, right. On this same section I assume that the charges are kept on the surface, right. So the charges are of course kept on the surface because this is a conductor, and if I take the charge direction, so any point on this one that I am going to measure will be xi prime, and the radius of this tube or the wire is actually equal to a. Therefore, the vector which joins the source point xi prime and the field point xi is actually given by xi square plus a square. Okay. So because of this, right, I can actually go back to that potential calculation, potential at any ith section V of xi, which is equal to 1 volt given by 1 by 4 pi epsilon naught. Now instead of using the equation, I will actually use the formal equation where I am assuming that the charge rho si will be constant, and you will have some a d phi dx, okay, which is the way in which a cylindrical surface area will be defined, divided by xi square plus a square under root. If you evaluate this integral over the range 0 to 2 pi and over delta Li, okay, you will see that you can show this as an exercise, that this is given by rho si a divided by 2 epsilon naught log of delta Li by 2 plus this quantity in the brackets. Okay, so it's a little complicated quantity, but this is a very straightforward integration that I ask you to do this one as an exercise. So plus a square plus delta Li square divided by 4. So this is essentially the quantity that I have, and if I further assume that a is much smaller than delta Li, that is I am assuming a thin wire approximation, then this complicated expression can be rewritten as rho si, okay, times a divided by 2 epsilon 0 2 times log of delta Li by a. So this would be a finite number that you can calculate. Of course you don't know what is rho si, but that is okay because the coefficient for that ith section will be this a by 2 epsilon naught 2 log of delta Li by a, and please remember all these sections will be the same. So your modified coefficient matrix Z matrix will instead consist of 4 pi a by epsilon naught, because there is a 1 by 4 pi epsilon naught, you have to multiply this by 4 pi by epsilon naught over here, log of delta Li L1 by a, and so on for all the other cases. Okay. So this would be the modified Z matrix, which will not have infinities on the diagonal elements because we have removed that infinity on this one. Okay. The unknown vector rho s1 to rho sn remains as it is. The right hand side vector 4 pi epsilon 0 4 pi epsilon 0 will also remain as it is, and you can now apply any matrix solver in order to solve this matrix, okay, and to obtain the unknown parameter rho s. Before we conclude this method of moments, I would just like to point out that in these scenarios the value of n can be very large, sometimes it can be about 100,000, and in this case no one actually computes the inverse of the matrix Z inverse. Okay, there are powerful methods of solving matrix equations, none of them involve determinants or actual calculation of the inverse. Okay, so you do not calculate the inverse, you do not find out the determinants, because it's very difficult and computationally intensive to do that one. The common methods are either to decompose the Z matrix in terms of its lower and upper diagonal matrix using a Gaussian elimination process, or you apply an iterative solution such as some successive over relaxation or successive relaxation methods. Okay. So, coming back, we now have a matrix and a vector equal to the known vector. Okay. So, this is say the known potential V prime or V or just for that case. Okay. And then you can use powerful matrix solvers to determine the unknown rho. Okay. All these elements are known to you because everything else, delta L1 is known, delta L2 is known, everything else is known in this particular matrix, and you will be able to find what is the corresponding unknown vector. With that, thank you very much.